Hi, happy Thanksgiving, everybody. I hope everybody's having a good day. Or if you don't even celebrate Thanksgiving, well then I still hope you're having a great day. Not really going on much here. It's kind of it's been a little bit quiet the past couple of years. I think the pandemic really kind of slowed a lot of kind of stuff like that going on. I don't really have any plans. I think everyone kind of doing their own thing this year. I was planning on just quietly getting ready for surgery next week, but you know, that's not happening this month, so hopefully either, you know, next month or January, more likely. If things go according to plan. Things go according to plan, it'll probably happen in January or February. It might happen in December. There's a whole bunch of moving parts to it, and it's kind of difficult. I really just want to get this over with and move forward, but we got a lot of stuff to keep ourselves busy. Yesterday I went on a 2-hour bike ride again. A lot of uphill on that one. It was pretty rough. You guys don't remember because you weren't there. But if I imagine, like, when I'm out there, like, because I'm a little cray-cray, I imagine, like, when I'm out there riding my bike that I'm, like, live streaming it. I don't know if other streamers do that. Like, they probably do. Look at how yellow my teeth are. Because I'm drinking black tea. It's a metal straw because of filtering the tea loose leaf. Some people use the metal straw just for a metal straw. Like, it doesn't make any sense to use the straw when, I mean, I guess, because apparently it'll stain your teeth less, but it doesn't make any sense because you're gonna put it in your mouth, and when it's in your mouth, it's gonna cover everything. You'd have to be like swallowing it, like you'd have to be like swallowing it, like as soon as it enters your glizzy overdrive. Yeah, we're not glizzying today. You know, that's for later. Today, we're going to be learning some Z80 assembly. Because honestly, you're going to have to know assembly if you're going to do any kind of retro game development. I don't care how many people think that you can get away with just using C and C++. You absolutely need some assembly at the very least. Ideally, the whole thing would be an assembly, but you actually have to, like, you know, not blow your brains out. You need to be able to learn assembly to have certain parts of your program become extremely efficient, because there's a limited amount of space that you can use in these retro hardware. There's a limited amount of RAM. There's you have to be able to optimize. Otherwise, your game is not going to be able to run as well as you want it to. It's not going to be as the kind of quality you want it to. And some games are only written in assembly. Plus, I've always wanted to learn assembly so that I can understand how programming actually works. I kind of have an idea from studying C. There was a series of lectures at Stanford that's available on YouTube that was talking about memory aligning. You know, it's basically just zeros and ones. It's basically just like setting aside spots in memory to do certain functions, to do certain things. Like adding and subtracting is really just adding a negative. And you have to have like a sign, like a bit that tells that whether it's negative or not, a bit that tells it whether it's adding or multiplying, and dividing is really just multiplying by an inversion. So multiplying by a decimal. You know, and a sign that tells it if it's a decimal or not, a floating point, integer. A sign that tells whether or not it's a character or a stream of characters. You know, there's all these different, like, you know, you can set aside in the memory whether or not it's pointing to a memory spot. You know, there's all sorts of different. There's all sorts of different functional things that happen at a hardware level, and I just can't wrap my mind around it. My whole life, since I really first started getting fascinated by programming, you know, like probably like 25 years ago, or, you know, when my dad would bring home his computer stuff and I just saw him, like, there's a big giant like book that he would bring, and there was like a Red Hat book and just like C++ and all this stuff that I would be really fascinated by, and I would try to learn. I could never really wrap my mind around it, so it's been a lifelong struggle. I can understand how to use the tools. I can understand how to set up an operating system. I can understand how to set up an editor and like a development environment and compiling things and, you know, utilizing scripts and all these sorts of crazy things that, like, you know, you need to know. So at the very least, I'm not at the very, very, very beginning, but it's just like understanding how the actual like architecture works. Like, what is actually happening when you type in a line of code? Like it's so like abstract, and for the most part, you don't need to understand it, you know, because you don't need to understand how a car works in order to drive. However, I just feel like I don't even know what's going on. I don't know how to make an application. I don't know, like, I understand that, like, okay, well, there's like, if you have like a desktop application, you know, you need separate, you know, you're basically putting a whole bunch of different applications together. Like, you have like a, you know, like a one that works with your desktop environment, you know, whatever that's coded in, so you have to understand how that works. And then you have to, like, okay, well, now that you have that, you have like a whole bunch of different features. Like, are you gonna open up and edit a file? Is it a text editor? Like, is it a web browser? Is it a what's your purpose? And all that kind of stuff. Or is it game development? Are you trying to make a video game? But then it's like, how do you design a game? And it's like, okay, I have an idea over what I want for a game, but how do I actually make that happen? Like, what actually needs to happen? How do I make artwork? Okay, that's a whole other ball game. Like, you know, and, you know, it's like, I don't think I have to be like a genius artist or a genius, you know, I am like not a genius, I mean, maybe, but, you know, I am a lifelong musician. So like the music part, I'm going to be using Mask to make, like, you know, NSF files and stuff like that, you know, or whatever is needed. I want to do Game Boy Advance, but I prefer the sound of the Game Boy Color. But with the Game Boy Advance, you have a more expanded sound chip, so I'll be able to utilize more sampling and all kind of stuff. So I'll be able to do more. But for my game, I want to have a more retro kind of Game Boy Color feel, even though the graphics and the ability of the game will be more like in depth. But in order to understand ARM, which is the Game Boy Advance chipset, I'm going to start with Z80, because that's what a lot, like, the Game Boy Color used, or the Game Boy, and the Game Boy, and a whole bunch of other stuff, like, I guess, like MSX and all sorts of stuff. And there's also the 6502, which is what the NES uses, and then there's a 65186, I think was what it's called. That one is for the Super Nintendo, but also you could do 6502 for the Super Nintendo, but the 65186 or whatever it is is basically like an HQ version of that. So I also have to understand the sound chips. I have to understand the graphics, what the graphics capabilities are, understanding all these things will help unleash, like a whole bunch of different stuff of understanding as a hobbyist, because I'm not trying to get a job. That's not, maybe eventually, maybe I'll be better off in the long run, like I would prefer, if I was hiring a programmer, I'd rather hire a programmer who understood like different chipsets and fundamental programming theory than someone who just like, is hot off the tutorial hell, who only knows how to write code in like C# and doesn't understand how it works, but like knows how to do stuff and deploy stuff. So that person is definitely useful. But if I was gonna hire like a developer to like lead my team, however, I have to actually have some projects under my belt, and I feel like the homebrew community is a perfect opportunity for me because I am a lifelong retro gamer. In fact, I stopped really enjoying gaming as soon as that era kind of ended, but it's not over. There's definitely a large community of homebrew enthusiasts, of retro gamers. There's speedrunners, and there's always a need for a speedrunning game. Okay? So, if I can design a game that's really fun for speedrunners, and by fun, I mean that it's not trivial, that it has replay value, that there's multiple ways to speedrun it, there's multiple challenges, there's different, that it's actually enjoyable, and that it's not just like based on memorization, that it's skill based. I think that's a huge part of speedrunning. A lot of it is memorization, and I hate that, which is why I'm not a speedrunner. I hate that like so many games are basically just memorizing like where all the glitches are and like, trying to make it as fast as possible. That doesn't really appeal to me. I would like a game where the higher skill you have, like a game like Dark Souls, for example, that's a skill-based game. And obviously there's always memorization and speedrunning and all that kind of stuff. But, a game like Dark Souls requires like some fundamental skills in order to actually speedrun it. And I feel like the speedrunning community for the retro gaming community needs more. There's always room for more. These people are addicted to finding the next speedrunning challenge. Okay, and instead of being a speedrunner, I could be the speedrunner designer. Okay, I could design the speedrunner games, okay? Because I'm a bit slower in thinking. In programming, it doesn't matter if you get it right fast, it matters if you get it right. Because once it compiles, it's done. And I gotta edit it and test it a lot, but I got nothing but time. But my biggest challenge, I'm selling myself short. I do understand a lot about computer programming and different chipsets and stuff like that. I just don't know how to use it. And, I'm gonna try my best. There's plenty of knowledge on the internet. We're gonna start with Chibi Akuma. And I set up a development environment already. Because for assembly, it's really difficult to work with assembly because you're working with chipsets that are pretty outdated. So you have to rely on emulation, but compiling different chipsets is difficult. But Chibi Akuma developed a bunch of dev kits in a very easy to use way. And so I loaded up a copy of Windows XP, specifically stripped down just to focus on development. And I did this yesterday. I really kind of get addicted deploying systems. It's like, I'm really good at setting up environments. So, I mean, that's also a skill, by the way. So right here, you know, I finally got everything to work. I needed to install DirectX, and I needed to just install .NET Framework. That's why the sprite editor didn't work. But we're not at the sprites phase at all. That's finishing touches kind of stuff. A lot of people kind of work backwards, I think. They kind of focus on the graphics and the music first. You want to get the game to work first, so this says Game Boy Dev, but it's the Z80. And so basically, Chibi Akuma set up a series of just sources and tools, and portable version and a portable deployment of Notepad++ that is set up to just you know, let me open up the file here. If I go into my Game Boy sources, or what's the oh, build. Or build ZX. Oh no. Sources all. And I think there's like a minimum deployment somewhere. I closed it. I don't know where the minimum deployment is. Or where's the hello world? That's not it. Oh, minimal, here we go. Is that on it? Huh? I actually made a new folder. Okay. I don't even know how to get started. That's the problem. Like, I'm just relying on what's already built. File history. What am I thinking? Oh, never mind. Then my history is not. Doesn't have all the stuff that starts out with. I don't know how to get this started. ASM 1. It's just. Error? I don't know how all this works. I know that these are different functions, but like when you first load it, it has like a minimum environment, and I have to be able to have that minimum hello world code working. You know what I can do? I can actually just be lazy and just back up the Notepad++ file history, file history. Config session. Yeah, just copy the session.xml. That's one way to do it, I think. Well, let me look at this. Let me look at it. I don't think that's it. Original file, last modified timestamps. There we go. I think that's it. I think that's it. Okay, so if I copy that over... Yeah, replace it with the 421 bytes, because I deleted a bunch of stuff. Okay. Oops. So if I open this, now it should have... Yep! Now it has the minimal.asm. But which... What's the file path? Sources 20. Okay, so it's just the minimal in 2021 tutorials, and that's not loading. Multi-platform Arcos Checker Lite. Opcode not supported. Okay, let me figure this out. I think I just need to back up the entire thing. Okay. Let me just do that. Okay. Let me unmount it first. Or there is like a backup.bat. What's that? Oops, not print. First of all, Z drive remove. Okay. And what's the backup do? Backs up all your it backs up the files that are already there. Okay, so I just need to delete all these and then just paste the backup files in Z80 DevTools. Okay, now when I open it up, oh oops, I need to mount it again. Okay, here we go. Okay, now it's working. Yeah, I think there was a problem with the emulator. And then I can yeah, because I had it like in a nice setup too, like where it's like. Is there a way to keep it scaled? I guess not. Oh. Window size 4x4. Or let's do 6x6. 5x5. Yeah, that'll work. Yeah, okay, now we got that working. Okay. So what's even happening here? So we include the Vasm build compatibility and the Win8 build compatibility. So how did the... That's just to, you know, we're not really... I don't know, we could look at all that. That's just to make sure it works with the emulator. So that's the hardware of the emulator. And if we look at those, source all, Vasm build compatibility. Okay, what's even happening here? It's an assembly file. Macro print. Okay, so that's using... I think there's like source code for Vasm. So if we go into the MU... Hey, what's up, Kojiza? We're going over some assembly code and stuff. Is this for Win8? I don't think there's any source code available for here, for Vasm or... so Vasm and Win8 compatibility. This uses some macros. Just basically, it's just aligning specific... I guess you can make like... So you don't have to code this every time, you know, you need to be able... You can, I need to... I want to look at the source code that this is... So it's like... Oh, it's just making macros. So it just changes... Print and write, and you just write lin, or align 256, align 8. I guess that's just utilizing the I don't know what this means without looking at the actual syntax of this. So let's also look at the Win8 build compatibility. Yeah, it's just like making like little shorthand, I think. Because, you know, normally you would just say a line 2 or a line 4 or a line 8, because these are different bits that these functions are assigned to, and this just makes them into a macro in order to be compatible with that assembly compiler. I mean that assembler, which makes it easier to read, because you know, you're aligning to 256, but you just say, you know, you could just write align 256, or you can write, you know, as a single macro. I'm guessing that's what that means. And this is for new org value, and it does new org point position. It defines value. Yeah, I'm not really sure what all this does, but we don't really need to know. Oh, quick header.asm. Okay, let's also look at that one. Quick header.asm. So this is when you're okay. So it checks to see if you're either doing build CPC or doing build ZXS. CPU compatibility. I think that's... I think that might be... That might be where it's defined. Okay, it just loads the different ones. This is like a header. This is like a header file that just loads all these different ones. So if I want to build, for example, let's just build ZXS. That's Z80 compatibility. Because we got to start with Z80. That's just the natural state of the chipset. Okay. So and this is GBZ80. So this is EJNZ. Where is the little cheat sheet I had? Didn't I have like, oh, no? There is... Oh, there's the cheat sheet. Oh, oops, I opened it up in eCaliber. That might actually work really well. But how do I zoom? Oh, oh, there we go. Yeah, this might actually be better because now it's like I can go page by page. And I can look at this one. Yeah, this might be a lot better. These are all the different assembly codes I need to learn. Let me move the oops. Let me move that out of the way. Put it down here. I suppose it's fine where it is. Yeah, so these are basically all the different opcodes. Opcodes are where the chipset is located in memory, I believe. These are all hexadecimal. So that's like the opcodes and how many bytes, you know, like ADC. I think this is all related to addition. Oh no. I think that's add carrier. Yeah, I need to like learn. This is just a cheat sheet, so we're gonna be learning what all these mean. Yeah, this is for pixels. 80 bytes are what the hardware uses. Oh, this is for graphics. Yeah, these are the different colors that are available. And their hardware numbers. And there's 32 colors. Oh, there's the all the font. And I guess I don't know what that additional colors or. Okay, here's all the different, what the commands mean. Okay, add C is add register R. Yeah, let's add the carry. The register and number, 16-bit register. Register, these are just adding. Bitwise and register and number. Okay. Yeah, there's a lot of different commands. And we need to know how they work. So there's a beginner series we're going to be going through. And there's multi-platform. And I guess these are some example games. Oh, sprites and tiles. Pixel plotting. Yeah, these are some... oh, Tron. That's, I guess, the bike game. Shibuakuma source code and how to change it. Yeah, it says it's like you go through Here's some details on the ZX spectrum. Yeah, we're specifically aiming to learn how to use the Game Boy Color, which, you know, it builds on the stuff that you learned before. So, you know, I have to learn all this stuff first, and then I can adapt it for individual chipsets. So that's why we're going to be going through the beginner series. So this is basic Z80 commands by example, but there's an introduction. Okay. Welcome to my assembly programming tutorials. These will be split into parts. Okay, so this is all based on the Z80 on the Amstrad CPC via WinApe. Next few chapters are quite technical. I don't even know technical stuff. Explain, but you can come back later. Okay, well, we're gonna start just from the introduction. I want to understand how all this works. Yeah, so we're using BASM in my environment here, that using the dev tools that and then this is going to be for CPC. Yeah, this is the Amstrad PC that that the tutorial uses. Oh. Oof. How do I disable that splash screen? I guess there's no way around that. So every time I compile, oops. Every time I assemble, I guess, it's gonna show that splash screen. So how about I just put it over here? Oof. Nope. Okay. Okay, 4 megahertz 8-bit processor. Yeah, everything is built on what came in the past. 4 million commands a second. Okay. Yeah, I've always wanted to understand assembly because it goes down to like the basic structure. And I feel like if you understand how to work with assembly, it kind of informs you how to work better with C++ and stuff. Because you're thinking about the end product. Because you really, assembly is just using a CPU at the hardware level, which is what C++ and other languages are actually doing. It's creating assembly in a more readable and workable, like with predefined libraries, or creating your own libraries that are basically macros for assembly. So if you understand how assembly works, it can kind of inform you how you construct your C++ code. So you can be more efficient and have less memory leaks and other problems like that. But I mean, you know, I'm not like at a graphics designer kind of level. Unity is like, you know, that's like one of the latest and greatest, but honestly, especially with the stuff that happened with Unity lately, probably want to go with something else. Assembly gives you the power to understand. No operating system, no drivers. Take control of everything. What's this? Oof. Yeah, that's what we'll be working with. We'll be using magnets to change every single bit in this. Yeah, this is what we'll be programming. We're gonna be changing all these different electric flows. Oh my god. Yeah, it's a maze. Yeah, basically we're gonna be shrinking ourselves down and we're gonna be walking through this. In order to change, we have to actually go flip switches like we're in Doom. That would be cool to make. Imagine a game that's actually like you walk around the CPU chipset as if it's Doom. But really what you're doing is you're traveling through, and there's teleports, of course, to make things sane, to go through different areas to go flip switches. And you're actually like in a first person mode flipping individual bits. That would be insane. Because then you could actually program using it. You could... that would be so cool. Just to see that work. Like if you had like a Doom style FPS game that allows you to run through these like it's like a big map. And like individually change different stuff. That would be interesting. I don't think we're quite there yet, but this is what we'll be working with. It's a bunch of different registers in memory to store electricity. And you're basically flipping switches to either deny, like, you know, have one or the other on, or both. And it's a big map of electricity flowing through things. See, like, these are the switches, I believe. Like, these are the switches, you know, this is like the energy source or whatever. And it all goes in here. And there's 1, 2, 1, 2, 1, 2, 1, 2. So this is 4 bits, I believe. Oh, looks like 1, 2, 3, 4. There's like 2 extra ones. Yeah, I don't know. But yeah, it's like this 1, 2, 3, 4. And you can have, or no, 1, 2, 3, 4, 5, 6, 7. This is 8 bits. And when you turn all of them off except for this one, you go put the electricity through here, which then routes itself into here. And then that, there's a whole bunch of switches inside of here. And I don't even know how to navigate this. But it goes that way or it goes this way. Holy shit. Yeah, this gets really complicated really quick. There's like millions and millions and millions of combinations here. So you can't possibly go over each individually. I mean, I guess you could. But I don't need to like I can't map out each one. But I can map out the starting points. So even at the basic level, even like working with the literal binary system at the hardware level, even if you just used magnets to move over switches, you're still working at like a higher level than what the actual hardware is doing, because you can't possibly work with all this. You have to work with these magnet switches. So you'd use the magnet to move these switches, which change the directional flow of these operational memory. And it's basically just electricity going through a whole bunch of different pathways in hardware. And let's see, like, what is this actually? Like, this one's smaller. 1, 2, 3, 4, 5. I think I was reading about that one, you know, at one point. We're gonna learn each of these individual chips. Yeah, so all those little green things are different bits. And inside of there, it's like 1, 2, 3, 4, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, wait, what? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Like, 22, and then 24. Okay, so there's 24 bits per. I guess this is a byte, or. So if you turn off all of the, okay, so if you turn off these, okay, I don't know how this works. Yeah, we're just gonna kind of keep that handy. I'm sure we'll learn everything about that. I'm sure. Assembly development can be confusing at first. It has very few commands to learn. Everyone has to start simply, so try to compare what you're doing. So try not to compare what you're doing to others. Oh god, easier said than done. I've been doing that for so long with everything. Just look at what you're achieving. Yeah, I try to focus on that because I am achieving things, a lot of different things in my life. Way more than I give myself credit for. Like, holy shit, I'm about to have my surgery. I'm so thankful for that. If I'm going to be thinking about being thankful for Thanksgiving, even though it's delayed, it's just because the surgeon doesn't want me to have complications. So I need to, I'm doing the work that's going to make that better. And according to my research, obviously it varies depending on different situations, but the work I'm doing, I'm actually doing more than this, but if I went on an hour walk every day for 5 days a week, like an hour walk 5 days a week, that would lower my A1C by 0.5%, which is 0.2% more than what I need. So I would be even better than what the surgeon wants. And if I just keep this up, because I'm doing like 2-hour bike rides, I haven't been going on so many walks unless I'm going on short walks to like the grocery store, on like my rest days and stuff like that. I'm doing bicycling instead. I feel like I can go longer. It's less impact than walking, but also because I have like a blister on my heel because I tried out some new shoes, but they were a bit, one of the right foot was like causing some blistering, and it'll like kind of heal up, and I might need to just get, and I'm using my old shoes until further notice. I might just have to take the L and get some, you know, order some new shoes, but like a size larger. But it's easier to ride my bike because I don't have to worry about blistering. So it's been easier to ride my bike. Plus, riding my bike is actually like way better for preparing me for surgery because it like works the pelvic floor a lot, which is where the surgery is going to be taking place. So I should be, if I take my test in December and it's down to 6.5, I'm going to shit. Like, seriously, that's like the healthy non-diabetic range. I mean, that's kind of the higher range. Non-diabetics are like 5.5 to 6.5. But if I can get it down to 6.5, holy shit, I'm gonna have good results. I'm gonna heal a lot better. I'm gonna have a much easier time recovering the lower my A1C is. The healthier my body is. The stronger my body is. So I'm doing all that. I'm thankful that, like, I even have this option to get this insanely expensive surgery that I'm gonna, like, let's face it. If insurance didn't cover this, I'd be entirely screwed. And I don't want to think about where I would be if that was the case. I don't even want to think about that because I am struggling just to get through things as it is. Even with all this these amazing opportunities. So, anyway. God, why does it keep doing that? Okay, what is the Z80 and what are 8 bits? The Z80 is an 8-bit processor with 16-bit data bus. What's 8-bit? Well, 1 bit can be 1 or 0. 4 bits make a nibble, 0 to 15, so that's 16-bit. 16 numbers. 2 nibbles, 8 bits, make a byte. Oh god! Is that where it came from? You're just taking a little, it's like you bit something, and then you took a nibble, and then you take a bite, and then you make a word. Blah. Holy shit, I didn't even really think about that. It's kind of interesting. 2 nibbles or 8 bits make a byte, so no, it holds 0 to 255. And 2 bytes, 16 bits make a word. It holds 65,536 numbers. And what is 65535? Well, that's 64 kilobytes. In computers, kilo is 1024 because binary works in powers of 2, and 2 to the 10th is 1024. Yeah, there is we could do an entire stream on how to on numbering systems. I took fundamentals of math, and we really focused on that for a while, and it was fascinating. It took me a while to understand, but I now know how number systems work. Because we live in we use like a decimal system, which is a base 10. But if you use a base 2, which is binary, it means that every single place, like if you have 4 places, in a decimal system, that would be thousands. But in a binary system, that's 0 to the first one on the most left number is 0 times 2. Oh no, it's, if you have a 0 there, it's 0 times 2 to the 0, which is anything to the power of 0 is 1. But if it's a 1, it's 1 times 2 to the power of 0, which is 1. And then the next one is 1 times 2 to the power of 1, which is 1 times 2, which is 2. So if you have both of those on, it's 1 plus 2 is 3. If you have the third one, then it's 1 time, and you only have 0 or 1 because it's a base 2. If it was a base 3, you'd have 0, 1, and 3. And then you'd be able to have 3 different numbers, 0, 1, or 3, or 0, 1, or 2, if you were a base 3 system. But if you're a base 2 system, you can only have 0 and 1. So if you're in the third digit, it would be 1 times 2 to the second, which is 4. So you have 1 times 4. So you'd have 1 plus 2 is 3 plus 4 is 7. And then if you have the fourth one, it's 1 times 2 to the third, which is 2 times 2 is 4, times 2 is 8. So you have 1 plus 2 is 3, 3 plus 4 is 7, and 7 plus 8 is 15, which gives you 0 through 15, which is 16 different numbers. Okay, Z80 is 8-bit, so it's best at numbers less than 256. It can do numbers up to 65,535, 2 more slowly, and really big numbers will be much harder. We can design our game around small numbers, so these limits aren't a problem. You probably think 64 kilobytes doesn't sound much when a small game now takes 40 gigabytes, but that's because modern game developers have gotten lazy. There's no need to worry about making games small anymore because everyone has 10 terabytes. Yeah, that's kind of the problem, actually. People have so much leeway that they're making shortcuts, and you can tell, and you know the players can tell that if developers aren't lazy, those games tend to do a lot better. You have so many different glitches and problems because people are just saying, oh, well, I have all this different stuff. I can just, make a whole bunch of different code because I don't have to worry about, you know, limited CPU usage and hard drive space. So I can just make a whole bunch of bloated, like, things that form, because basically I think like what happens is you have like all of these different things that you can store in memory. And so what happens is you can create files that are then stored in memory, and a lot of those are going to be graphics. But you have to be able to utilize those, and there's like a whole bunch of stuff that, like, if you understand how to use the architecture efficiently, it's going to be better. And if you don't, because a lot of the time you don't need to understand the architecture, because it gives you so much, there's so much more leeway. You don't have to worry with working with just 8 bits. You're working with like 64 bits, right? So you have like a whole bunch of different stuff you could do and not worry about as much memory leaks. Whereas, like, you know, an operation would leak over to a different spot in memory. You have 64 different bits rather than 8. And then they're even getting into 128-bit CPUs, you know, 256-bit CPUs. But right now we use 64-bit CPUs mainly. You know, that's what, you know, you have x86 is the main CPU that we use, the main processor, and there's a 32-bit one which we use for the longest time, and we have backwards compatibility for it. But most modern architecture is based on 64 bits. So right now, and this can change in the future, especially with quantum computing, which changes everything. You know, with the architectures we have right now, x86 is the standard, and it's 64-bit, which means that if you want to utilize x86 64 CPU, you have a whole bunch of different bits to use, and memory leaks are less of a problem, because if you're a bit lazy and you assign certain bits for some functions to map into memory, and then, you know, 64-bit, it exponentially allows a whole bunch of storage and operations. And so, like, you're going to be using a certain operation, it's going to be using up certain spots in the memory, because you use the 64 bits and you put them in a bunch of different... from my understanding, you have 64-bit architecture. It means you have like a big slice of memory, and we can have like I have like 64 gigabytes of memory, which means I'm not going to run out of memory, pretty much. I'm not going to have to worry about memory leaks. But back in like the Amiga days, for example, the story of Amiga is pretty amazing. Because it was a bunch of like amateur, like, you know, like it was a bunch of like random hackers taking like the Motorola 80800 chipset and like just having at it, just hacking away at it. And yeah, I mean, this goes beyond this, but memory leaks were a huge problem, and you'd have to actually, it was integrated into the Amiga operating system on the desktop that you would clear memory, because the system would just crash constantly because you would run out of memory. And, you know, so memory, like utilizing memory, it's still important, because as things scale up, it doesn't mean that you can just still be lazy, because it means you're going to have less to work with if you're inefficient with it. If you're more efficient with it, it means it's going to be even better. It exponentially, like, yeah, like you can get away with a lot more, but if you were to treat the new architectures as if you treated the same way that you treated the old architectures, you'd be taking full advantage of the chipset's tech capabilities. So, like, you know, that's where true passion and design comes from. So numbers in assembly can be represented in different ways. A nibble, which is half a byte, can be represented as binary 0000 to 1111. So it's 16 decimals. or 0 through F. Yeah, so we use hexadecimal because it represents a nibble, which is 4 bits. And if we have a byte is 2 nibbles, so that's 8 bits. So usually we organize things in 2 hexadecimal numbers. So we'd have 0 through FF, 00 through FF, which is like that's that big number. It goes 0 through the 65,000 number. Yeah. Oh no. No, that 0 to 256. I mean. And a word is, 2 bytes. And that's like what a lot of more, like 16-bit systems. Like that would be like the Super Nintendo and Genesis chipsets. Whereas 8-bit uses 0 to 256. And I believe these numbers just represent spaces in memory. Also, a letter can be a number. So yes, because that's how you... Think of hexadecimal as being the number system invented by someone with 15 fingers. A, B, C, D, E, F are just numbers above 9. Decimal is just the same. That's why we have decimal system. If people were born with 8 fingers, we would use an octal system. Like our whole society would have been based on octal, pretty much. Or people would have probably still used decimal by going 1, 2, 3, 4, and then like 5. They would go like 0, 1, 2, 3, 4, or like 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, 9, 10. Like that's how people would have counted with 4 fingers. I think 10 is an easier number to work with, but you never know how society could have evolved if we had 4 fingers. Maybe we would have used an octal system. It's possible. And then what would programming look like then? It would have been developed a lot faster. Because if we developed an octal system, that means we would have developed binary much sooner than we did. I think binary came about in the 1600s or something like that. Like, people didn't come up with alternate numbering systems for like a while. We used a base 10 system without understanding how it worked, because we have 10 fingers. So it's just, I don't know. It's just kind of interesting thought experiment. Decimal is just the same, it only has 1 and 0. Or did he mean binary? In this guide, binary will be shown with the percent symbol. So percent 11001100. Hexadecimal will be shown with an ampersand. So and FF. Yeah, so that's 255. Assemblers will use a symbol to denote a hexadecimal number. Some use $ or FFH or even 0x, but this guide uses ampersand, as this is how hexadecimal is represented in CPC Basic. All of the code of this tutorial is designed to compiling with the WinApes assembler. If you're using something else, you may need to change a few things, but remember, whatever compiler you use, while the text-based source code may need to be slightly different, the compiled bytes will be the same. Another way to think of binary is what each digit is worth. Each digit is a number, has its own value. It apostrophe S. Let's take a look at percentage 11 at binary 11001100. So that's different bit positions. That's what I said earlier. So that's 2 to the power to 0, 2 to the power 1, 2, 3, 4, 5, 6, 7. So it would be 0 plus 0 plus 4 plus 8 plus 0 plus 0 plus 64 plus 128, which is 204. If it's a good thing we have calculators. It's a good thing that the CPU does this for us, because we'd have to manually do it each time. If a binary number is small, it may be shown as binary 11. This is the same as binary 00000011. Also notice in the chart above, each bit has a number. The bit on the far right is 0, far left is 7. Don't worry about it now. Yeah, that's just exponents. Look at Windows calculator, switch to programmer mode, has binary and hexadecimal view. Yeah, so you can just use, a calculator, and you can just easily, programmer. If I want to figure out, like, what number, like, 52,345 is, it's hexadecimal CC79, and it's binary 1100 1100 0111 1001. Or it looks like this. Ah! Or octal 146 171. Yeah, if you want, you see, this is like, if you want to actually work this way, you could actually like start, just switching individual bits. This is like a good way to like look at what like switching out certain, like if you want to have a byte here, if you want to see like what doing specific bits will do, because I think it's better when you're thinking of CPUs to think about the hardware. And if you're thinking about hardware, you're not thinking about numbers, you're thinking about switches. So if you think like, okay, what happens if I turn this switch on? It goes 64. So then I know that switch is aligned to that. And then if I turn both these switches on, it'll be aligned to a new number, which is a whole new function. And if I like align that to this image that we looked at earlier, like if we have this, like you can say that like, oh, if I have this switch on and all these other switches off, it means that I'm blocking the electricity flow from this. I believe that's what it means. No. It means I'm opening up this one. So the only thing opening up is this one. And then when you open that up, like if I only have this bit open, it activates all this. Only like I mean, this is so microscopic, you wouldn't be able to see it. Like, it goes through here, and it bypasses. See, otherwise, these also go here, but it goes to like both. And this one just goes through here, and it only allows these different pathways. I don't know. And all of this, either way, no matter what you use, it also goes into here. Or no, something else also goes to this one. So this bit is used by something else. So if I use one of these other chips, and it happens to bring the pathway up here, it accesses this bit right here. These 4 bits. It accesses these 4 bits right here. So there's like a CPU that's attached to this one. So whenever these bits are used, it also, you know, or whatever this one's attached to, like a freaking maze, whatever this one's attached to, I don't know if it, I think it might be bidirectional. So if this is on, it sends out a signal, and the other one sends a signal, I guess? I'm not sure. I don't really know. I don't even know what this CPU is. I mean, what this... I don't even know what this chip is. There's a whole bunch of different chips. Like... or a whole bunch of different, like... memory chips, I believe. Okay. Yeah, so we can always just use this calculator. You could always just use this calculator to find out. Okay, this is 32 bits. This is just a byte. And this is just, yeah. Yeah, we're only going to be working with 8 bits, so we only have to worry about these 8. I believe. And then we add these 2 together. But then again, that's what makes a double, a word. Yeah, we're going to be working with words at the most. Which are 16 bits. Okay, so here's where it starts to actually become programming, when we start to have functions. But wait, I said a byte could go from 0 to 255. What happens if you add 1 to 255? It overflows and goes back to 0. Same happens if we add 2 to 254. If we add 2 to 255, we'll end up with 1. This is actually useful if we want to subtract a number. Yeah, subtraction is really adding. So if you have this number plus yeah, I don't know. So negative number is FF. What? Oh, right. You add 1. That's why there's always an extra byte to the side to tell whether or not you're adding 1. Oh no, whether or not you're adding 255. Wait, what? Oh no, there's a whole extra byte to tell how much you're adding. So if you have FF and you add what? Why is there a 2 here? Yeah, I don't know. All these number types can be, don't worry, your symbol, okay, you can type, assembler knows the same thing. Yeah, it depends on what you're trying to do. If you need more help, check out convert.base on the tools.disk. It's a hex binary calculator. Well, I can just use this. But there is one. So if I go into sources, what was it called? Convert. Doesn't seem to be here. Okay. Hello? It doesn't look like it's here. The hell? God damn it. Okay. Yeah, there is no convert. Dot basic. On the tools.disk in the source file. I don't know what he's talking about. There is no convert file. Jeez. Okay, it doesn't really matter. I have a calculator here, but it's just kind of bizarre. He says there's a convert.basic file. Oh! It's not a file, it's a tool. No? Utils? Or is that in the emulator? Okay. Okay, yeah, we're just going through the introduction first. We're at the Z80 now. Okay, yeah. Numbers and assembly, and then we get to the getting started in the beginner series. Okay, okay, working with numbers. We know what numbers we can have on the Z80, but how do we work with them? When we need to save our results, we will store them to that 64K of memory mentioned earlier. But the memory is in some distance away from the processor. To be fast, we want to use the memory built in the processor. This Z80 memory is called the registers. Okay, so registers are just memory of 0 through 65,535. There's not much of it, but it's really fast. So try to use them to do as much as you can. Each register can only store 1 byte. But some registers can be paired. So HL together are 16 bits and can store 0 through 65,535. Each of the registers has a purpose. Of course, you can use any register for anything you want, but they all have strengths because many commands will only work with certain ones. And some commands may be slower and need more code if you use the wrong one. A is used for calculations, like accumulation. F are the flags. We don't tend to use this directly. What's this question mark? Some weird alternative. Alternative encoding for the font. It's set by mathematical operations, and we respond to its content via conditional jumps and calls. HL, this often stores memory locations, as there are a lot of special commands that use it to quickly read or write whatever memory locations. It's also good at 16-bit math. So if you want to add 2 numbers above 255, you'll probably need it. BC, often used as a byte count or a loop counter. Okay, that's how to do like how many times you've gone through a loop. Like if you want to do 4 operations, or yeah, like, you know, like if I is less than 32 or something, then it'll do it, you know, 32 times. 0 the first time, and then if you want to do something like 10 times, you do it for I, you know, for I is less than 10, because it'll do it 0 through, it'll start out with 0, then it'll add 1, and then it'll do it to 9. Sometimes you'll use B and C together for a count up to 65,535, or just B on its own for up to 255. Okay, DE is destination. If you're reading from one place and writing to another, you'll probably use HL as the source and DE as the destination. Okay. Okay, IX is sometimes we want to get to memory by specifying a relative position. Indirect registers allow us to do this. For example, if we have sprites and each 4 bytes. Let's have pizza. Hey, Crack Miser. I can't have pizza. It's too many carbs. I have a strict diet. I'm out of kale for now. I have to go shopping again. I have a bunch of canned spinach though. So I'm using spinach instead of kale. I know it's not ideal because it's canned spinach, but using spinach instead of kale until I can go to the grocery store again. And I'm gonna have to get some turkey out of my bank account instead of my food stamps, but because I'm like out of food stamps, but it's okay. I need the protein. I need the lean meat. It's like $16 for 3 pounds. I think I might have enough. to get, I don't know, I don't have enough to get through the whole rest of the month. I don't think. But, I don't know, I'll figure it out. I might just get some eggs. I don't know, I'll have to figure that out when I go to the grocery store. Okay, so IX specifies a relative position. So it's not a, so it's like if you're at position somewhere, it'll say like where you want to go to memory relative to where you are at. Indirect registers allow us to do this. For example, if we have sprites in each 4 bytes for X, Y, width, height, just point IX to the start of the data or the sprite we want and read the rest out as IX plus 1. Oh, okay, so you just tell IX where the start of the memory. You don't need to map out the whole thing. That makes it much faster. Don't worry about this, we'll explain it later. Okay. Yeah, that's when you use, that's when we're going through those different registers, interrupts, and all that. Multiplication. Yeah, this is what we're learning. The Z80 chipset. iWay works the same as IX. Oh, but it's like IX and IY. I see. PC, this is the place in memory that the Z80 is running. We don't change this directly, but call, JP, and RET all affect it. Call, jump, and return. Oh, like when we say like return 0 in C code. It returns to the very beginning of the memory when it's done. Zeroes everything out. SP, this is the stack pointer. It points to a big temporary store that we'll use for backing up values. We need to, okay, so that puts things into RAM. Stack pointer. So we put a value in, we put it into the stack, and then we make another value, and then we utilize the other one in the stack. This is the refresh register. The system users know when to refresh the memory. Don't change it. You mess something up. But it can be used for getting simple random numbers. Oh, okay. This is the interrupt point. On the CPC and MSX, pretty useless. They can use it as a temporary store. On the Spectrum is really important. You'll have to leave it alone. Okay. So for CPC, we can actually use this register for temporary storage. Okay, so the main registers A, and so we just have accumulator, we have flags, byte count for BC, DE. Oh, it's because it's the hexadecimal that's sorry. I don't even know. IXH and IXL. IYH and Y. Oh, because you have 3 letters because you have, this is when you get into, you have 2 sets of 8 bits. And if you use all 8 bits, you can get 3 letters. You know, because normally, yeah, I don't know. Stack pointer is SP, refresh is 0R, interrupt vector is I, program counter is PC. Then we have some other flags, some other registers. You have sign, so to say whether something's positive or negative. You have a 0, you know, 0 flag. This might be like for a bit for true or false. what do they call it? Bitwise? No. Booleans. This might be for Booleans. Because zero, if it's a zero flag, it's either zero or it's not. So that might be for true and false statements. Half carry is used by DAA. I don't know what that is. Parity and overflow. Use if sign changes because the register is too small. Okay, so that's for overflow, to keep the number. N is add and subtract, and C is carry and borrow. Format of Z80 commands as follows. So command destination comma source. Add brackets around this register pair like HL means address in register blank. So LD parentheses HL comma A means load A into the address in HL. Whereas LDHL comma hex 4000 means hex 4000 means load hex 4000 into HL. Okay, so that loads a value into HL, and you use the parentheses to load A into the address. And LDBA means load A into B. Special addresses. Happy Thanksgiving, neat dreams. We're doing some assembly language stuff because I'm a noob. I need to go back all the way down to the beginning of programming in order to understand it, because I have tried so many times over the years to understand higher level code. I think the way my brain works, I need to understand like raw things first, and then I work my way up, which makes things a lot slower. I mean, I understand my autistic brain pretty well, I think. And I think it's just I have to do the work, because if I don't, I just can't really work with things most of the time. That's why things are so difficult for me. I try to bypass things whenever I can, but it means that, you know, with a lot of things it doesn't particularly matter. You know, like I can try to bypass. I don't need to know everything all the time, but if I want to learn something to be able to work with something, I have to kind of go back and slow down and go from like the ground up, because otherwise I just don't know how to work with things. And with programming, you need to know how things work. At least I do. I am still struggling to grasp after all these years how programming actually works. And I think just working with these like basic like retro chipsets, especially since I grew up on like the NES and the Game Boy and stuff like that, I think learning how to use these can be pretty fun. And I might be able to make my own games, which is the goal. I have some ideas, but I have to be able to implement the ideas. Yeah, assembly, basically, yeah, if you want to do the Commodore VIC-20, yeah, exactly. There might even be an, you can go to chibiakumas.com to learn the Z80 specifically, but, oops. You can learn assembly programming. It's assemblytutorial.com. There's a whole bunch of different chipsets, because the way assembly works is there are like kind of unified commands for assembly, because it's really just bits. It's just zeros and ones. But you need to know the architecture standards of the hardware that you're coding for. So if you want to code for like Amiga or like Neo Geo or the Sega Genesis or whatever, the Atari ST, or you know, just a basic 68K Motorola, then you're gonna have to learn Motorola assembly, 68K assembly. If you want to code for like, let's see, you're trying to do the Commodore VIC-20. Commodore is going to be 68K, I'm pretty sure, because the Commodore was made by Amiga. So you're gonna need to learn Amiga assembly, pretty much, I guess. But I let me see, Commodore. But here's the that's, you know, Commander, yeah. Yeah, there's like the RISC-V open source CPUs. There's the EZ80, is like an enhanced version of the Z80. So if I'm learning the Z80 right now, 65816 is the enhanced version of 6502. So that's like the Super Nintendo and the Apple II GS. Yeah, so the NES is actually built on an Apple II. Yeah, jumping from hobby to hobby. I mean, as long as you're having fun, what does it really matter? I mean, unless you're trying to become a professional, then it becomes a vocation or a skill. You know, that's a little different. But I got a lot of stuff going on for me, and I'm going to be exploring. I've been exploring, but I'm going to be pursuing a different kind of vocation than this. This is more of a hobby for me, so I don't really have a time limit. I'm not trying to become a professional programmer. I'm doing this as a hobby because I really want to be able to make my own things, just for fun. I need to learn how to do that instead of just doing something because I think it'll make me money. If I want to make money, I got other things I'm working on, which I think can be very enjoyable in the chosen pathway that I'm going. It's still more work, you know, but I'd rather do that than this. I don't want to try to compete with all the programmers out there. I can't do that, but maybe I could compete with other models, I think. And I think I would enjoy that process more than this process for making it a profession, because this process as a profession would be hell. I work so slowly, and I don't think I'd be able to compete with all the people out there in the IT world. I just don't. I could, but I don't think it would be worth it. I think it would be absolutely terrible to try to compete in the programming world for as a profession, as a main income. You know, maybe eventually it could become more than a hobby. But that would be like, I don't want to rely on that. I'm going to rely on my ability to perform because I'm a performer. I understand performance from a very early age. Singing, playing musical instruments, some acting, although I do want to take an acting class. And I need to learn how to properly, you know, I need to improve as a model. But those are things that I can't really explore at this exact moment. It's coming up soon. Hopefully sometime next year I can start really advancing in my modeling career. But as far as all this goes, if you want to program from the Commodore, you're gonna want to use the 68K. So I'm gonna link you to that. Because Commodore is made by is what made Amiga, and Amiga uses 68K. So if you want to program for the Commodore, you're gonna have to learn 68K. And you know, there's different stuff here, you know, getting started and stuff. But this, I don't know. I'm using Z80 because this developer seems to have made the most resources, and the beginner's tutorial is in Z80. He seems to have the most experience with the Z80, so I'm going to use his tutorials for that. But you could just get started with the 68K, and there's plenty of resources for programming for the 68K. You know, you can just, you know, Google it. You know, there's a whole book. I have a giant book. I can't find it. It might be, it's buried somewhere. But I have a book called, like, you know, like there's a whole bunch of different 68K guys. Yeah, I have this book, Programming the 68K. But let's say you want to program for the Commodore Commodore VIC-20. It uses VIC Basic, but it also uses an assembly, and I mean everything does. Oh, it uses 6502. Okay, so actually, you wanna learn the 6502. Yeah, the VIC-20. What am I? It's right there. Never mind. Here it is. This is what you want to learn. If you wanted to program for the Commodore 64, you would learn 68K. But because I think when the Motorola chip came out, it revolutionized computing. That's when the Amiga came out. The Amiga revolutionized desktop computing. It didn't last very long, because then, you know, Microsoft Windows came out, the Intel chip, the x86 came out, you know, like whatever. What is the x86? CPU. Yeah, it's made by Intel and AMD. Intel came out with the x86 processor, and that's what ended up taking the market, because it was just Microsoft took over, and you know, Microsoft is Microsoft. So and Intel was, you know, Intel and Microsoft really took everything over. Yeah, so you can learn 6502 assembly, but in order to understand assembly, you have to actually learn how it all works, and so that's why I'm going through. I do want to program for the 6502 because the 6502 is what the NES uses, and you can use C or Basic in combination with assembly, and the more you can use an assembly, the better. But this guide is written for the Z80, which the Z80 is like the Sega Master System, the TI-83 calculator, the MSX, which is like the Microsoft. I mean, this was the big one. The Z80 was for MSX, which was like really popular in Japan. The MSX was like really popular in Japan and Europe, I think. But I think like mostly Japan, from what I understand. Like, let's say, Wiki MSX. Yeah, it was made by ASCII Corporation, and we all know what ASCII is, right? They have the standard, and it's made by like Sony, and you know, so it's like a Japanese system. Yeah, it had an MSX Basics and MSX DOS. Yeah, the Sony MSX, Hitbit. Yeah, there's a whole bunch of fun stuff. You can get lost in like retro computing. It's a huge hobby, and it can get expensive, especially if you want to, you know, get refurbished original hardware. But we don't want to do that because I don't have that kind of money, so we're emulating. But if you really want to get into it as like from the original hardware, there's a whole giant community on YouTube and everything. If you want to make that into even your creation, like if you even want to like make a whole YouTube channel based on it, then that's one thing. But regardless, you still need to learn the computer programming, and emulation is sufficient. It's not the same as working on the original hardware, but I think we can live with it. Yeah, don't get compulsive on eBay, Neat Dreams. Don't do it. Don't get compulsive on eBay. Give me that money. Just kidding. Give me the money. Neat dreams. Don't waste it on eBay. Give it to your favorite content creator. You know, because otherwise you're just being irresponsible with your money. If you have time to be watching Twitch, you can afford $5 for a sub. Just kidding. 4 different bootleg Famicoms? Uh-oh. Everything's bootleg now. Like, even Nintendo uses an emulator. Like, they use ROMs. It was found that, like, on the Nintendo Wii, for the virtualware, they used actual ROMs that were available online from pirated software. Because they didn't have the original one, I guess. Like, like someone used an actual ROM that had like a ROM header rather than the original header in order to design Super Mario Brothers for the Nintendo Wii. I don't know exactly what the story behind that is, but like, come on. Okay, so where were we? Okay, yeah, we basically have just basic commands. You're putting on the right side, you're putting one register into a destination in memory. That's basically that is everything that assembly is. You're using one of these registers, which has like a function, and you're placing it in a place of memory. Or you're loading it either directly into memory or into an address. Special addresses. There are some special addresses on the Z80 processor that are common to all Z80 systems. RST0, which is hex 0000, RST7, which is hex 0038, and NMI, which is hex 0066. So you have reset, IM1 interrupt, and non-maskable interrupt. So the reset, usually the first command executed as the system restarts. That just sets everything to 0. The RST7, reset 7, is called by interrupts, usually V blanks, that resets the screen, right, in video memory, in interrupt mode 1. NMI is non-maskable interrupt, is a special interrupt which can be caused by connected hardware and cannot be turned off with DI. Okay, so this is like how you add like from serial ports, like a keyboard or a mouse or a controller, to tell if something has been connected, I believe. These may be ROM on some systems, like SMS, MSX, and ZX Spectrum. This will make using a custom interrupt handler in IM1 difficult or impossible. So basically, like if you have like MX Basic, right? MX Basic. MSX Basic. It's a dialect of the basic programming language. So what programming language really does, the reason why there's different versions of BASIC is because the architecture on the CPU has a very specific set of instructions and memory mapping. And so what the language does is it basically makes little macros so that you can do it faster. But in the end of the day, you're really just doing all this kind of stuff. You know, you're really, you know, writing all this kind of like, you know, doing different like, you know, LD message into HL. You're calling print string, you're calling new line, and calling loads different macro functions from some header files, I believe. Like if we look at Yeah, all that kind of stuff. Hey, what's up, Jess? How you doing? We're doing some nerdy computer programming assembly language stuff for the Z80. Error. Jess Matrix has entered the Matrix. I hope you're doing good. Don't self-destruct. Don't do it. Purpose of the NMI address will differ depending on the system. For example, on the CPC and ZX Spectrum, it's not typically used. Multi-phase 2 stop button will cause an NMI interrupt. Okay. And call address 0066. In the master system, the NMI is more important, as an NMI interrupt occurs when the pause button is pressed. No, don't do it, Jess. Yeah, just a big giant, like, it's like a user manual. It's not like a tutorial. It's like a big manual. Like, it has all the specific, like, everything that it's capable of. But you have to know how to use it. And a lot of it is just trial and error, really. Everything is so dumbed down now. But that's because it assumes it's from the work of the people who did that. So that people, people can work with, like, you don't have to invent a car every time you want, like, when you want to drive. You can just buy a pre-made car. And so, like, it's really good that we have these, that we're standing on the shoulders of giants. Please notify manufacturer and wait 3 to 5 business days. Self-destruct sequence failed. Yeah, the thing is you kind of have to have experience. And I'm sure people did write tutorials back then, but it was just so, like, trial and error back in, like, the original programming day. Like, the original programming was like those punch cards, and then all the stuff that came out in the 80s, that was actually standing on the shoulder of those giants. So all this assembly language was actually dumbed down version of programming to begin with. Like, this is already dumbed down. Like, all this code right here, like, this is just faster versions of what people in, like, the 40s and 50s would do. Right? In the 60s and 70s. And then, like, in the 80s, like, a whole bunch more advanced chipsets came out, and so it became way too much to handle. And so people came up with assembly language to work with the machine language. Like, the assembly language is actually higher level than the byte code and, like, the machine language. Yeah, all code's dumbed down. It's really all just ones and zeros, and until we get into quantum computing, but then even then that's just zeros and ones at the same time. But wouldn't that make it, like, ternary? I don't know. It's not the same as I don't know. Quantum computing is a whole different ballgame. Yeah, this is like... But yeah, like, they originally had to, like, move those bits, those little switches to allow the bits with actual magnets. And they had to actually, like, program things with hardware instead of typing things out. They would have to actually, like, move hardware around, and then it got more and more complicated, and you had to have more and more layers of abstraction. And now we have chipsets that are so advanced that we can still work with assembly. That's the cool thing about it. It still scales. But if you really want to get anything done with these advanced chipsets and what we have learned to be able to do with them, with like really advanced systems, you need higher level languages like C and C++. And C works closer to assembly than C++ does. C++ is really just it's like C with extra steps. It's evolved into its own kind of thing, but originally it was just C with extra steps. Okay. So we also have these addresses. Yeah, these are special addresses. We have reset 0 through 7 and NMI. Game Boy Color. The Game Boy is not a Z80, but it's similar in some ways. However, the Game Boy GB Z80 CPU has no IX or IY and no shadow registers. We're becoming the Game Boy's weirdness more later. Shadow registers are a copy of the main ones. On the CPC, the system firmware uses these during interrupts. If we stop the interrupts, then we can use them for even more power. Interrupts do things like read the keyboard and update the system, but we can replace the firmware and take over these jobs ourselves, and take total control of the Z80. Yeah, those were like really. My dad had some of those. My dad had some of those books, and I remember being fascinated by it, and I couldn't figure it out, obviously, because I didn't know how to set up compilers. I didn't know all that kind of stuff, but I know all that stuff now. So now I have no excuse. I'm an adult. I'm adult. Okay, I'm adult. So I have no excuse. I have to actually just go in and do the work. But that's what I'm doing right now. Okay. And I'm going to be taking a break soon. I just wanted to finish with this introduction, and we're going to do lesson 1, and then I'm going to head out. Because you can't do too much at once. So compare commands and branches. If val2 is greater than equal to val1, then go to label. So it's comparison greater than equal to. The different architectures will have different, like this is the basic, like if you're going to use basic. It's a comparison greater than equal to, less than equal, or less than greater? What is that? So on the Z80, this is CP val2. This is JPNC, comma label. This is JPC, comma label. JPZ, comma label. JPNZ, comma label. But it's BNE label, like, you know, BC on the CMP val2. I mean, on the 6502, this is like BCS label. And then on the 68K, it's like BCC. It's pretty similar. These are switched on the 68K. Is the BCS is greater than equal to, but BCS is the less than on the 68K. This is comparing two values. This is whether it's greater than equal to or not equal, I guess. I guess that's the same as not equal. Yeah, NE. BNE. Bitwise not equal. Bitwise compare. I don't know what S and Q equals. Bitwise equal. Bitwise compare C. I don't know what the C would be. And then bitwise compare subtract. I don't know. But they're switched in the 68K from the 6502. 6502 and the 68K must have came from the 6502. This might probably what happened. Okay, now we're getting started with Win8. For our Z80 to melt, we're using the WinUp Armstrad CPC emulator. It's free and does everything you need for development in one place. Works great in WinXP, which is where we're doing our development environment with the custom folder structure stuff. development environment that he specifically designed. So we're working with that. Okay. You may want to develop for the ZX Spectrum MSX. You start with the CPC and WinApe. WinApe has a built-in assembler and debugger that are second to none. Yeah, so using WinApe to do all your programming and debugging to start. In the early days, you will make a lot of mistakes and having the because if I'm working with other things, the tools might not be as useful. So with the WinApe, I have the debugger, the assembler and debugger inside of it. It has the compiler, the emulator, and the debugger in one place. You can even develop MSX and Spectrum code with it. The MSX and Spectrum versions of Chibi Akumas are compiled in WinApe too. Yeah. If you don't use Windows, WinApe works okay with Wine. We're not doing that. We're doing XP. So, you know, that's why I have these scripts that just kind of do that for me. All the compiling can be done in Notepad++. And then if I wanted to debug it, look at the registers that are being used. Yeah, and we're gonna learn how to do all this. How all that works as time goes on. I just do a little bit at a time, little here, little there, and I can do it on stream, I can do it off stream. I kind of like doing it on stream because it keeps a record of things. You know, we can see my progress over time, and I can look back and say, wow, look how stupid I was back then. And then later I'll be like, wow, look how stupid I was back then. I'm a CPC blue screens. We can start straight away into basic. Yeah, so you can actually code directly into WinApe. So if I just open up WinApe by itself, it just goes straight into basic. Oh. Oops. Yeah, I don't know how basic works. We're working with assembly. It assumes you know nothing. See, it's like this tutorial assumes you know nothing. So, you know, we're gonna get there. Let's not jump ahead of ourselves. We can show the assembler, okay? Yeah, so we can even like, this is what's going on right now, I guess. Yeah, this is the hello world. Oops.
I need a status report.
Self-destruct sequence has been initiated. We've got an incoming transmission.
What?
Patch
Pushing it through.
Assemble.
How are you, gentlemen? We have successfully acquired your base of operations. Prepare to be destroyed. 1 minute to box destruct. How?
Yeah, so if we want a new assembly, we can actually just do assembly directly in here. But we're using Notepad++ for that. And then loading it into the assembler
Captain, what should we do?
through a batch script.
Initiate launch sequence. Open the pod bay.
Because if you look at these batch scripts, we're doing CPC. We're doing VSM CPC. That actually loads a script. I don't know where. Vasm cpc.bat. Oh, it goes into Vasm. Okay. So if we actually want to load that to look at what it does, the batch script, we go into the emulator, go into Vasm. Oh no, it's in utils. We go into utils, we go into Vasm, and we can look at all at the batch scripts that we have. Why is there a new folder? Wait, what does it do? Okay. Vasm cpc.bat. Utils Vasm cpc.bat. Okay. Vasm cpc.bat. So if we look at that, it loads Vasm Z80 old style Win32.exe. Does all these kind of assembler things. And if it has errors, then it abandons, and then it does something. And then after it runs this, it removes a batch script from memory, I guess. Let's look at if we actually load that assembler into CMD. What is it called? Vasm Z80 old style. So if we load, we go into utils, we go into Vasm, which is the assembler. Vasm Z80. Vasm Z80. Old style 132. We actually load this up, and I think, is there a help file? Oh. No input file. Oh. Oh no, it's gonna use slash, I think. No? Could not open help. There's probably a manual here somewhere. Let's look at them. Let's try to find the manual for the Vasm. Yeah, so this is like actually how we go into how the assembler actually works. We want to know all the different options. So if we wanted to compile, assemble, to compile everything with customization, we'd have to go through here and understand how that works. We don't really need to know how it works. It's already pre-configured for us. But if we wanted to start out from scratch, we would have to know how to compile these, how to assemble these. We would have to understand how to use Vasm from scratch. And luckily, he does it for us, and he runs this in a script for us. With these flags. And so we made all these batch scripts to make things easier. Oops. Okay, now let's get straight into it and code something. Okay, click on the assembler menu and select show. Okay, we're gonna do it directly into WinApe, I guess. We might just be able to do it direct in Notepad++. So if we do a new and we save as, and we have our, make a new folder. We go to Rebecca. Okay, and this is going to be lesson 1. Okay. And we do org ampersand, this is hexadecimal 8000, and we do LD 4 into A. We increment A. I don't know, ink. What is it, ink? I guess he'll explain all the commands. And then we increment A. LD, we load 10 into B. We add B. And from LD A into address of hexadecimal 7000. And then we return. Okay, and let's see if that loads up. Oh, it doesn't, because I have to have the minimal system if I want to do it directly. So what I need to do is I need to actually start up WinApe. You redeem the thing to make me dab? Oh, I see it now. Yeah. Make me dab. Yeah, I see it in Cheddarino. Oof. Okay, so if we press F3 to open up the assembler, we do new, or let's close this. Let's open the one we already made. And then we run with F9. I guess it doesn't really output anything. Okay, yeah, 0 errors. You'll see the assembler output. This shows the actual bytes of code that what you typed ends up as. Check there are 0 errors. If there are, then you made a mistake typing. Click on OK. Now this is the magic of WinApe. Your code is now immediately in the emulator's memory. So let's run it. Now go back to the blue screen and type in call. Okay, so yeah. And then you call that. Okay, so you org that space in memory and then you call it. So when you write assembly language, you can then call a function in memory. Okay, so that's how you do it. Okay. Call ampersand. Oh, if I can. Yeah. Okay, it's actually 6, even though on regular keyboards is. Yeah, they're different on the cubes. Call. So exclamation point is still 1. 2 is actually quotation, double quotes. 3 is still hashtag. 4 is still $. 5 is still percentage. 6 is ampersand, and 7 is single quote. 8 is left parentheses. 9 is right parentheses, and 0 is underscore. Hyphen is equal and minus. Okay, and plus. Okay, so plus is actually an up sign. And euros if you do shift. Okay, so call ampersand hexadecimal 8000, and it runs it, I guess. We run the debugger. I don't know. Basic should return the message ready. Something else happened, check your code. So if I change the code, if I break it, if I accidentally put like an extra comma here, well, first of all, it'll have an error. If I do something else, like, I don't know. Not really sure. Okay, congratulations! I officially kick ass. Yay! I can dab again. Okay, so let's kind of see what everything does here. So this org sets the origin of the code in memory. Z80 is a 16-bit address plus. So memory goes from ampersand 0000 hexadecimal 0000 to hexadecimal FFFF, but we can't just use anywhere. As hexadecimal 8000 is a good safe area on the Amstrad. For your code to start. Okay, so LDA comma 4. Load A, the accumulator, with the number 4. The accumulator A is the main register used for calculations. Registers are used for very short-term memory storage. Increment A. Increase, not increment. Oh, the same. Increase A by 1. A will now contain 5. Increase A by 1. Hopefully you can test it now. Contains 6. Set B to 10. B is another register. It can't do as much as A, but it can do a lot. Notice the destination is on the left and the source, the number, is on the right. This is always the case with the 80 assembly. Okay, add B. Adds B to A, although A isn't mentioned in the command. Since the accumulator A is used for almost all maths anytime a destination isn't mentioned, it will be A. Okay, LD address of hex 7000 comma A when brackets call it parentheses. I guess there's no square brackets, so I guess parentheses are brackets, parentheses are used in assembly. They define a memory location. Oh, I forgot to add more notes. This command could be written as add a B. When Ape will compile this. But the A comma is superfluous, so you're better off learning not to need it. Okay, brackets are used. Because it's content of that memory point. Oh, okay. Okay, hex 7000. It is the A number. Is the content of that memory point. And then ret returns back to whatever called the program. In this case, basic. Phew. Now if I don't include ret, and I call it what? Oops. I guess not. I guess it just returns it to it anyway. Still, if your symbol open, just click on this window. Click on the get air. Okay, I can. Oh, I can make a breakpoint. Okay. It means before the Z80 runs the command LDA, 4, it'll stop and the debugger will appear. Okay. There we go. Yeah, that's how you run a debug. You run the program, and when it hits there, it'll load the debugger, and you'll be able to see the memory code. So we have nothing on all the other things. These are storing stuff that are reserved for the system from 0000 to 0044. It has predetermined things. But at location 8000, we started our own. This is empty memory. And now we've reserved it for our own code. Otherwise, it's all 0. I don't know. It says like greater than like lightning bolt. Do I need a special font installed? Or is that just kind of ghost code? Okay, that's what it's supposed to be. It's like that in his too. Oops. Okay, and if you've done everything right, the debugger will immediately pop up. Okay, top of the screen you see the compiled code. On the right you can see all the registers. And then there's the stack. These are the status of the registers at this breakpoint. If I were to step through the code, how do you step? Oof. Oh, and there's also stuff predefined way over here too. Because you have the code that you're compiled, and then it goes into access of, it goes into spots of memory, and it performs those operations. Registers. Our code uses A and B. A is the first half of AF, and B is the first half of BC. Okay. In the middle of the screen, you can see the memory. Okay. At the bottom of the screen, you can see the ROM and other debugger options. In the bottom right is the stack. Debugger has a ton of options we're not going to use right now, but feel free to try them later. Try right-clicking on things for more options. Okay, and then you can run it from there. You can even change the registers of memory by typing new values in. So if I want to, I can actually go change AF. Let's change it to 0069. Oop. And then oh, didn't do anything, but crash emulated memory be erased. You have to reassemble your code from the assembler. Okay, let's look at what it does. Oh, okay. Yeah. So you can actually run it on single step with F7. Okay. Yeah, single step is F7. Oh, and then it jumps to the locations to do those, and then it jumps to the location to do those, and it jumps to the location to do those, jumps to the location to do those. Okay, so it's all loaded in memory beforehand. And you just change out some of the numbers. It loads them into memory, and then it performs them. Performs a whole bunch of operations one at a time. Oh no, it's looping. Oh no, it's not. And that's the end. So with that small amount of line of code, we just performed all those operations. Okay, you should see A change to 4. Okay. So if we press F7, okay, yeah, we see on the right it says AF is now 0468 instead of 0068. We press F7 again. Now it's 0500. And press it again. And 0600. And if we press it again, now it's 1010. And then return this change. This one, the pointer counter changes from 800A, 800A from, and then now it's going through the standard encode, I guess. The debugger isn't just debugging your code, but the whole CPC, so you'll end up debugging the whole of BASIC. Okay, so yeah, it'll then like start debugging the actual like stuff that's running it in addition to your code. When your code is finished running, we have one thing left to do. Remember the program wrote to N7000. Scroll down the memory browser to find. Oh, okay. So that if I do this again, call 8000. If we run it F7, we step through. We step through a couple times, and then we call to 7000. Now, after we do that, if we scroll up and we go to hex 7000. Now there's the number. One zero. Just going to find. Yeah, there it is. In the stack. If we go to 7000, now what if we print 28,672? Oh. You should see our final value for A has been saved there, which is 10. Oh, because you increment A to put into B, and B becomes 6, and then you add 4, because A is initially 4. A is initially 4, you add 2 to it, and then now that's B is 10. And then you put let's add B to A. So Evan 7000 should actually be 14. if I go to 7000 right now, oh no, that's in here. Okay. When does it change to 14? Close it when you've seen enough. Okay, think back on what you've just done. You've written a program, compiled it, run it, and watched everything the program did at the CPU level. More detail than you've probably ever seen in a computer work before. Maybe not, but not bad for a day's work. Okay, adding a few numbers may not seem like much, but it's just the start. You'll soon find you can make the computer do amazing things. Also, don't forget, once you understand the basics, you can use pieces of other people's code to do the work you don't want to. These tutorials will show you how to build on the open source code of the Chibi Akuma's game to allow you to make big progress super fast. And I highly recommend you to type the programs in yourself. Yeah. Yeah, I think that was good for today. Okay, I can save it there. Yeah. Why is it like that? Okay. Okay, I think that was good for today. We've been going for 3 hours. Okay. 3 hours. Going cray. Yeah, I hope everybody has a good Thanksgiving, whoever's celebrating it. Today was pretty good, so I think that, you know, just little by little, don't really try to rush yourself. I think that's the big problem I have with computer programming stuff is I'll start to rush myself and I'll start to, you know, I'll start to burn out and just lose hope. And in general, that's kind of what a lot of the issues I have are. Not just in programming, not just in chess, not just in my life. A lot of areas in my life, I start getting really frustrated. And I just need to slow down and just do it. Because just do it. Make your dreams come true. Today was yesterday. Yeah, yesterday you said today. Yesterday you said today. Just do it. Do it. You know, because like otherwise, you know, eventually you may not get it right away. You may not understand what's going on, but eventually the stuff that you do starts to work, whether you understand it or not, whether you intend to or not. And that's the thing that's been getting me through these past couple of years, is that if you do the work, the results will come, whether you intend it to or not. And once you start to understand how things actually start to happen, you can start setting your intentions to like get those outcomes. And I'm slowly getting there. I feel like these past 4 years, I've just been trying to learn how to become a basic human. Am I artificial general intelligence? Am I trying to figure out how to be a person? Basically. But I'm an actual person, so it's not really like that. Okay, I hope everyone has a great day. I'm gonna try to just relax and go on my workout later, and then you know, read Tolkien, and maybe work on my novel. I don't know. We'll see where the day goes. I'm just like trying to get through and just do the work. That's really what these next few months are going to be about. Is now I have to actively work towards getting to this surgery. So it's going to be really difficult. But I got a lot of stuff to do, and we're going to have some fun, nerdy stuff happening, like coding assembly language and creating a Game Boy Advance game eventually. But we got a lot to learn. And hopefully I can learn a lot. Like, you know, it might be a lot of work, but it pays off. You know, it's not the same as just opening up like a C++ and just compiling it, but I've already done that stuff and I haven't really been able to do much with it. So if I understand how all these like assembly language stuff works, maybe things will start to click. Anyway, have a good one. Bye-bye. Happy Thanksgiving. Bye-bye.